Here we look at the physical principle of freefall, which is an application of motion with constant acceleration. And it's sort of the first physics that we're doing, the first physical law. Although the law that we'll talk about, that of gravitational acceleration, we'll find some other ways to write that in sort of a more general or a more fundamental way. But for now, we'll just describe an experimental fact, which is that of gravitational acceleration. And then we'll do two examples. So just a falling object and a rock thrown from a roof. Should make one quick note, which is that the word free fall is a bit of a misnomer, at least in sort of colloquial language. When we say fall, we simply mean an object moving near the surface of a planet, like Earth. The object does not have to be falling downwards. It could be going upwards, it could be going sideways. So free fall simply means an object which is free of other forces other than gravity. So what is gravitational acceleration? So far we've been doing mostly mathematics here, talking about vectors and then talking about kinematics, sort of the way to describe motion. But this is really a physical law about the motion of objects near the surface of a planet. And so let's just state this here. An object near the surface of a planet, in the absence of other forces other than gravity, moves with a constant acceleration down. So we could take our favorite planet, Earth, and if we're near the surface of the planet, then the planet looks flat. So you have to be close enough that the planet looks flat for this to be true. And maybe you're standing there and you watch an apple fall from a tree nearby. And what you would observe is that that apple would fall with constant acceleration. So it would take a path. Maybe it's straight down if it's dropped from rest. And if you were to describe that motion, you would assign to it an acceleration vector that points downward. To complete the statement of the law, the magnitude of the acceleration, which we usually write with the term g, and in fact g we will normally simply use for the acceleration due to gravity on Earth, although you could write g Mars, g Jupiter, depends only on the planet, not on the object. So this apple will be falling as well, but maybe, this apple will be falling with A, but maybe like your little cousin is also falling because they fell out of the tree, and their motion would also be described with the same exact acceleration vector, A, downward. So everything falls with the same acceleration. As my example above is meant to illustrate, the gravitational acceleration is the same regardless of the object's mass. So all objects fall at the same acceleration, and it has nothing to do with the properties of the object. There's a caveat here, which is sort of in the statement above, which is we assume no other forces. So if there's any air resistance, then this won't be completely true. It really pertains only to objects in a vacuum. And you can go find some videos online where you watch like an anvil from a blacksmith being dropped next to a feather in a vacuum, and they fall exactly identically. So on Earth, we can make a measurement of that acceleration. We'll show some ways in a moment how you can do that. You could time a falling object. And it turns out that the value of g for Earth is 9.8 meters per second squared. So what does that mean? It means that in the first second of an object's fall from rest, it will be moving with 9.8 meters per second as a velocity. And then in the second second, it will pick up another 9.8 meters per second, etc. So with every second that passes, the velocity increases by almost 10 meters per second. So let's do an example. Let's calculate the time for a basketball to fall to the floor from the rim of the hoop. So let's make ourselves a picture. So we have the basketball hoop, looks something like this. And it turns out that the hoop is exactly 10 feet from the ground, regulation, and that 10 feet is a little bit more than 3 meters, 3 meters, 5 centimeters. So we take a ball and we place it up there on the rim, and then we assume that it'll just sort of fall straight down. Although, as we'll see in future problems, it doesn't really matter if it falls straight down, and maybe we'll show that here. So it's going to fall down, and we'll assume that it has a 0 initial velocity. So our initial velocity has a magnitude of 0, and then when it hits the ground, it will have some non-zero velocity, v final. And if this is t is equal to 0, then we could call this t final, the amount of time that it took to fall. So this is a constant acceleration kinematics problem of the type that we just learned about for 1D constant velocity, constant acceleration problems. The only difference between some of the problems we've already done is that the motion is happening along a straight line that occurs vertically rather than horizontally. So we could choose whatever coordinate system we want. I could choose a coordinate system that looks like this. I guess I should have made it more clear, and I'll put my origin right at the ball. So that means that at the final point, this ball would be at plus h along the y-axis because I pointed my y-axis going down. So we're interested in the amount of time, and we are given the distance that it fell, and we assume, because of this principle of gravitational acceleration, that the acceleration is constant. So let's write down an equation for constant acceleration, and let's make it the position equation. So because I've chosen to have my motion go along what I'm calling the y-axis, I'm going to write my equation in terms of y. So that equation then is y final is equal to y initial plus v0y t plus 1/2 ay t squared. And I left out one thing, the most important thing from my diagram, and that is that we will assume that the object moves with a constant acceleration down. So I draw the acceleration vector pointing downwards. Okay, so let's apply this to the problem. So usually when you write down a kinematics equation, you should first write it down like it looks on your equation sheet, but then you should state how you're going to apply it. And maybe I'll just give myself a position A and a position B, so I'm applying it from A to B, meaning from the point at which it leaves the hoop to the point at which it hits the ground. And that allows me to be very clear about what each of these quantities are, the final and the initial quantities, because I know exactly where they occur. So the first thing we encounter is y, that means y final. So that's the final position of the ball over this interval, and we decided that that would be on the ground. And because of the way I've drawn my axis, the value of y at that point is going to be h away from 0 in the positive direction. So this number here, this tick mark, is simply plus h. So I can write plus h there. The initial value of y is up here at the origin, so that's going to be 0. Now my initial velocity in the y direction, I've chosen to make my initial velocity 0. If I had made my initial velocity horizontal, then I would get exactly the same answer, because the y component of that thing would also be 0. If I allowed my basketball to be moving upwards or downwards, then I would have an initial y velocity that was non-zero, and I would get a different answer. So I'm going to try and find the answer for a ball which is simply dropped from rest from the hoop. So my v0 in the y direction is 0. 0 times t is 0. And now I have 1/2 times the y component of the acceleration. Well, let's find that. So I should redraw my coordinate system and then take my acceleration vector and move it, without rotating it, over to the coordinate system. And what do I find? Well, this tick mark is what we call AY, and you notice it's on the positive y-axis. So my acceleration vector has magnitude g, which is 9.8 meters per second squared. That's because we're standing on Earth. And so this tick mark here is equal to positive g, because it's on the positive y-axis as I've chosen my coordinate system. So we can write AY as g. And then we have t. We could call that t final, because that's what I called it here. And we get t final squared here. So we applied the kinematics equation, and now we can just simplify it a little bit. So h is equal to 1/2 g t final squared. And my question was, what is the time for it to fall? So we can solve that for time. So t final is going to be equal to 2h over g, and then I have to take the square root. So I would have had t squared is equal to 2h over g. We take the square root of both sides. So what is that? Well, this is going to be about 6 meters divided by about 10 meters, 6/10. So I guess we should plug that into the calculator and see. So we have the square root of 2 times 3.05 divided by 9.8, and we get 0.79. So it takes just a little bit less than a second for a ball to fall from the hoop down to the floor of a basketball hoop. Okay, let's try another example. We have a rock that is thrown vertically upward with a speed of 12 meters per second from the roof of a building, which is 60 meters above the ground. When does it strike the ground? What speed does it have when it strikes? And how high does it go? So we want to do a couple of things up front, which I hope you're getting familiar with. We want to draw the problem so that we can sort of show ourselves what's going on. In doing so, we want to give names to all of the relevant quantities. So that includes the things that we are given, like this initial speed, but also things that we were not given, like maybe the height at which it goes upward. And then finally, for anything that is a vector, we want to draw that vector so that when we come to equations like this and we're asked for the components of those vectors, we'll be able to easily figure out whether they're positive, negative, or in the case of projectile motion that we'll do soon, whether we need to take some component of that vector. And of course, to take the components of a vector, we must choose a coordinate system. So we'll choose a coordinate system which will determine where we measure the x and the y positions from, but also will allow us to determine whether a velocity or an acceleration vector has positive or negative components. So let's do it. So we have a building. So here's our building, and the ground is down below. So I don't know how, I guess a 60 meter building probably has more than 6 floors, right? More like 20 floors, but oh well, there it is. Here's our building. And we have a person on top of the building, and the person is going to be throwing a ball upward. So that person is going to take sorry, not a ball, but a rock. They're taking a rock and they're giving it some initial velocity upward. which we were given as 12 meters per second. So I give it a name. I'm going to call it V0, V0 for time 0. What else do we know? Well, we know the height of the building, so I'm going to give that a name, 60 meters. And I guess that's all that we were given. But now, one thing that you usually want to do for this type of problem is to try and sketch out what the trajectory of the object looks like. So I'm going to draw the trajectory of the object. It's going to go up, but then it's going to reach a peak, and then it's going to come back down again. So I don't know too much about it, but I have some understanding of how things move on the surface of the Earth, and usually you throw something up, it comes back down again. So I can draw that. And now that I've done that, I see there's another thing I should label, which is the height above the roof at which the rock goes. And I don't know what that is, but I'll give it a name, little h, and then we'll try and find it. Let's label some of the other things that we were asked about. So if we call this t is equal to 0 here, then we might give some other times. This could be t is equal to t top, maybe. And this is t is equal to t bottom. Give names to those. We were asked about the speed when it strikes. So that's going to be the magnitude of a velocity vector of that rock when it hits. So here's the rock, and at the very end it will have some downward velocity. And we know that it's downward because we know that an object has a velocity vector that is always tangent to its path. So this will have a 0 velocity vector. We might also notice that at the top, the velocity at the top is going to be equal to 0. That's if it is moving exactly vertically. Even if it's not moving vertically, we could say that the velocity at the top in the y direction is equal to 0. So the vertical component of the velocity must go to 0 if an object is to be moving upwards and then downwards. It has to go through 0 at that point. So I think I've labeled just about everything. Now we need to make ourselves a coordinate system. So we have a lot of flexibility in choosing that. So we can choose to place it wherever we like, and we can choose to make it go point in whatever direction we want. And we can also choose to call the axes whatever we like. So I'm going to make a usual choice of calling the horizontal axis the x-axis, which we won't use here because the motion is completely in the vertical direction. And I'm going to call the vertical axis the y-axis, and I'm going to place the origin right where the object starts. I don't have to do that. I could have put it like down here, but I'm allowed to put the coordinate system wherever I like. So we're asked all these questions. How do we solve them? Well, we use our equations of kinematics, in particular constant acceleration kinematics, because, oh, I forgot the most important vector to be drawn, which is that at all times we have an acceleration vector that points downwards, and its magnitude is g, which is, of course, 9.8 meters per second squared. So I'm going to be using constant acceleration equations for all the motion here. So let's just try some things out. So when does it strike the ground? Well, it looks like we could, we're interested in a time, and we were given some distances, so maybe we can use this equation again. There. And how will we apply it? Well, we're given some information about it initially. We're given some distance information, at least for the height of the building, and we're asked about times. So maybe we can apply it from here all the way down to the ground. So from the initial moment to the moment that it hits the ground. So let's give those some names. So if this is like A, maybe this is B up here, and this is C. So I can just apply this from my initial moment of A to a final moment of C, just skipping B completely. And it should work because the entire time the stone is in flight, it is undergoing constant acceleration. There are no other forces on it. So let's see how that works. So y final is our first quantity here, and that means the y value at position C. So take a moment and figure out what that y value is. So notice this is my coordinate system here. So this is a y position of 0, and anything below, because I pointed my y-axis upward, is a negative y position. So this tick mark, the tick mark where it sits, where it hits the ground, is going to be a negative number, and it's going to be exactly equal to minus h, minus 60 meters. So the value of y is minus h. Notice that I give names to positive quantities. That way in the end, well, I can represent a negative quantity as minus a positive quantity, and in the end I always know that I'm plugging in positive quantities to my numbers. The same, most importantly, goes for g. G is a positive number. Okay, next is the initial position in y. Well, it starts out here, that's at the origin, so that's just going to be 0. Then we have the initial velocity in the y direction, the y component of the initial velocity. Well, this is the initial velocity, and you can see it points upward in the y direction. So, well, let's just look at its component. So that's the y-axis. I place my initial velocity vector on it, and this number, v0y, you can see it's a positive number, and it's equal to the magnitude of the vector, v0. So I can replace v0y with just plus v0. So those are different things. This is a component, which before I write down my coordinate system could be positive, negative, 0, all sorts of things. And this is the magnitude of a vector. It's a variable that I know to be positive. So I'm expressing that my y component of the velocity is a positive number now. Okay, what is t? Well, t is the time it takes to get to the bottom, and we called that t bottom. Then we have plus 1/2, and ay. Ay is the y component of this vector. So if we make ourselves a coordinate system, in acceleration, now you should probably make a separate coordinate system for accelerations and velocities because they live in different worlds. One is measured in meters per second, one is measured in meters per second squared. So this tick mark is a sub y, and its value is going to be negative, and it will be exactly minus the magnitude of the vector, so minus g. So I can replace ay up here with minus g, and t is again t bottom squared. So where does that leave me? Well, let's try and make this equation look a little bit nicer. So we have t bottom squared. I'm going to move it to the other side so that it becomes positive, and I get g over 2 out front. And then I have minus v0 t bottom, and then I have minus h, and all of that's equal to 0. So I said I wanted to make it nice. Why did I write it like that? Well, I recognize here that the thing I'm looking for is t. Everything else is known, right? I know what g is, I know what the initial velocity magnitude is, and I know what the height of the building is. But my unknown appears in a quadratic formula, or in a quadratic equation here. And so I wrote it in the way that one solves a quadratic equation. Remember, the quadratic equation is ax squared plus bx plus c is equal to 0, with a solution of x being equal to, and there's two solutions, so it's the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. Remember that? So that's how you solve a quadratic equation. Well, that's exactly what I have, except that it's an equation in t instead of in x. So I can write t bottom is equal to the opposite of b. So what's the opposite of b? Well, b here is minus v naught, so the opposite of that is plus v naught. And then I have plus or minus the square root of b squared, so v naught squared, minus 4 times a, which is g over 2, times c, which is minus h, so that becomes positive there. And then I have it all over 2a, which is 2 times g over 2, so that's just all over g. So we get, v naught over g plus or minus the square root of, and I could, if I wanted to, I could bring the g inside. Why not? So then we get v naught squared over g squared. I brought it inside, so I have to square it. And then I get 4gh over g squared, and also over 2. So that means 4h, well this I guess is going to be 2. So it's 2gh over g squared, so it's going to be 2h over g. 2h over g. Okay, so that tells me what t is. It's a quadratic equation, so it gave me two solutions. If you look at this, you can see that if h was equal to 0, then this whole thing would just become the square root of v over g squared, which is just v over g, and the v minus v would be a 0 there. But instead, you have something here, so that means that this whole thing is going to be larger than v over g. And that means that the one with the minus sign is actually a negative time. So what the heck does that mean, a negative time? Well, if this object was in free fall, not only after being thrown, but also before being thrown, meaning it wasn't thrown, it just happened to be moving upwards, then the negative time would correspond to the amount of time before this moment when it was down here. So it was like all going up and then back down again. So that would correspond to that. So what we're interested in then is going to be the positive time, and we can write that out. So t bottom is equal to v0 over g plus the square root of v0 over g squared plus 2h over g. Let's find out what that is. Plug it in. So our v0 is equal to 12 meters per second. Our g is equal to 9.8. Our h is equal to 60 meters. And that's enough for us to solve now. So v0 divided by g plus the square root of v0 divided by g squared plus 2 times h divided by g, close out the square root, and we get that t bottom is equal to 4.93 seconds. So the amount of time that it takes to fall is 4.9 seconds approximately. Okay, so we used an equation, we got a result from it. What else can we get? Well, that answers part A. What is the speed when it strikes? Well, we have constant acceleration, motion with constant acceleration, and we have an equation that tells us about the velocity in the direction of constant acceleration, and that is Vy is equal to V0y plus AyT. And if we apply that with exactly the same initial and final conditions as we did before, then we can use t to be t bottom, meaning we're using the amount of time that we've already calculated from the launch moment to the final moment when it hits the ground. And then we should be able to make a calculation of the final velocity in the y direction. So let's do that. So Vy is going to be the y component of v final, the vector that I drew here at the end. Well, v final, as we can see, because it points along the path, is pointing downward, and the y-axis points upward, so v final is going to have a negative y component. So I should write vy as minus v final. So that's how I show that it has a negative y component. The initial velocity vector, as we found before, it has a positive component, which is equal to plus 12. So that's why we wrote it as plus v naught here. So we do the same. V naught y is equal to just v naught. And ay, well, a points downward, so it's written as minus g. And then t is the same t we had before, t bottom. So now we can solve. We're interested in actually the magnitude of the final velocity. So let's just multiply the whole equation by minus 1. So that becomes v final is equal to g t bottom minus v0. So what does that give us? Let's plug it in. So we have g times the thing that we just found, and we subtract off v0. Oops, I screwed that up. Minus v0. Oh, I still screwed it up. So we have g times 4.93 minus v0. That's better. And we get 36.3, and that's in meters per second. And then we could say from the picture, the VF vector points down. So we assumed that it pointed down in order to calculate it. That's why we had Vy as negative. And we know that it points down because it follows that path. So if we're asked for the final velocity, then that's what it would be. I guess we weren't. We were asked for the speed, so our initial answer was perfectly fine. The speed is just a single number. And finally, we have what is the maximum height that it reaches? So that's a question about this little h here. So what can we do here? Well, I could write down an equation that relates the position, the y value, and the time, the amount of time that it takes to get there. And then I could maybe relate that to something else in order to find the height. Like the y velocity equation could probably do it. But it turns out that in a problem where you don't actually have information about the time, if you want to relate distances to velocities, then it's useful to use that extra equation that we have for constant acceleration, which is, remember, vy squared, v final squared, minus v0y squared is equal to 2ay y minus y0. So it's a combination of the position and the velocity equations that eliminates time. So let's see why that's useful. So I'm going to apply that equation, not from a to c, but now from a to b. So looking back at our picture, that means going from the throw to the peak right there. So what do we get? Well, at b, the final velocity, remember, is going to be 0 in the y direction. And that's because the object goes up and comes back down again, so the velocity vector must go through 0, at least in the y direction as you go through there. So that's a useful thing. When you reach maximum height, it means 0 velocity in the height direction. The initial velocity, we found that already. It's going to be a positive y component, and here we have to square it. Then we have the acceleration in the y. We haven't changed our coordinate system, so that's still minus g. And then final minus initial position, well, we called the final position little h, and we called the initial position the origin. So our equation looks like this. So we get, multiplying through by minus 1 again, we have v0 squared is equal to 2gh. Our unknown was h, so let's solve for that. So it's going to be v0 squared over 2g. And if we plug that in, then we get v0 squared divided by 2 divided by g, we get 7.3. And of course that's meters for a height. So we're able to find everything. So it went pretty smoothly for me here. And I didn't prepare myself to figure out exactly how to do that, but it just turned out to go pretty well. In these problems, you don't want to be discouraged. So if it turns out that you write something down here, you properly apply it from one position to another, and then you get to an equation that has more than one unknown, you shouldn't get discouraged that moment. You should instead write down another equation and try and find another true relationship from one point to another. So as you practice these problems, you'll see some sort of tricks of the trade, ideas about which equations to use given the information that you were presented with, or which equations might get you there the quickest, like this equation here, since I don't know anything about time. But in general, the method is simply to write down the equations of motion that you have and then see how they apply. And as long as you're careful, the thing that you get will always be true. And as long as you're persistent, you'll always be able to solve the problems that you're asked. One other thing I should mention is sometimes you'll get to answers that are out of order based on what is asked. So don't worry about that. Just find what you can, and eventually you'll be able to find the solution. Okay, that's all.